This week we have introduced the principle of stationary action. So we have started with few definitions. First, we define what was an event. An event is defined by a given position in space-time. So it has a position in space and a given time, like A and B in the top right plot. We have also defined a path which connects two events. So that's an evolution in space-time between these two events. We see here three different possible paths between the events A and B. And we have introduced the action. So the action is a number associated with a given path between two events. So it's obtained by taking the integral between both events of the Lagrangian along a given path. So when you change the path, you change the action. We have discussed the concept of stationarity. So in the case of a function, it's a familiar concept that when the derivative is zero, as shown on the left. And we have generalized this concept of stationarity for functional. So functional is a function of a function. That's the case of the action, because as you can see, it's a function of the path, which is a function of time. So stationarity of a functional is when you have a small change of the path, doesn't change in first order the action itself, then you have a stationary action. It's really equivalent to having derivative equal to zero. And when you have found such a path which leaves the action stationary, you have found the classical path. And we showed that indeed the principle of stationary action is equivalent to the Euler-Lagrange equation. Another important concept we introduced this week is the idea of symmetries and how they relate to conservation laws. So if the Lagrangian depends on a coordinate through its derivative but not through the coordinate itself, then we call this coordinate a cyclic coordinate. And when you have a cyclic coordinate, the associated canonical momentum, which we have defined as the partial derivative of the Lagrangian with respect to the time derivative of the coordinate, is constant. And that means that you have you have found a conserved quantities. That's associated to a symmetry, because if the Lagrangian doesn't depend on the coordinate, on the cyclic coordinate, then that means you can change this coordinate, you can do a transformation of this coordinate, you don't change the physics of the system. That's what we call a symmetry. So for each symmetry, for each continuous symmetry associated to a continuous transformation, you have a conserved quantity. Examples include symmetry under space translation. So if you perform an experiment at some position and you do it again at a different position, and if the physics doesn't depend on where you are doing this experiment, you should get the same result. And the associated conserved quantity is the linear momentum. Similarly, if you rotate your experiment and your physics doesn't depend on a particular angle, you have an invariance under rotation, then you have conservation of angular momentum. The case of time translation leading to conservation of energy is a bit more subtle, and we will discuss that later in the course.